Hello, welcome to Basics of Noise and its Measurement. This is the fourth lecture of the current week, that is the 7th week of this particular MOOC course. And over last 3 lectures we have discussed some of the practical elements related to noise measurement. We have discussed how to measure impedance of a material using 2 microphone method, how to quickly design a reasonably good impedance tube, and in the first lecture we had looked at some of the important considerations we should be careful about as and when we are taking noise related measurements. So what we will discuss today and also in the next lecture will be about octave bands and octave band analysis. To give you an overview as to why we are talking about these is that a lot of times whenever we report results related to noise on the frequency spectrum, people are typically interested in having some sort of a standard format for reporting these results. So if I have to report my results in different octave bands, then there are some industry and trade specific standards which we have to subscribe to, so that whenever I share my results with the larger scientific and industrial community, then they can understand those results and they can compare these my numbers with their numbers in a consistent way if we are following the same rules of the game. So that is the fundamental thinking behind defining industry and noise community specific standard octave bands, because otherwise an octave band could be anything. It could an octave band could be 3 to 6 hertz, 6 to 12 hertz, 12 to 24 hertz. These are all octaves, and mathematically the definitions of all these octaves are fine. But if I am having my results in 3 to 6, 6 to 12, 12 to 24 hertz and so on and so forth, and another person is taking measurements and reporting results in a different set of octave bands, maybe 2 to 4, 4 to 8, 8 to 16 and so on and so forth, then we cannot compare our results because his octave bands and my octave bands are different. So that is the first thing I will discuss, the definition of octave bands, and then we will discuss something beyond that how do we synthesize and compress data into octave bands and report a single number specific to a particular octave band. Okay, so whenever we are talking about standards, we either refer to ISO or ASTM or some well-known standard. So for octave bands, whatever discussion we are having, it will be in context of an industry standard, and that is ISO 266. So this is a document, you can go and purchase it online. It has been developed by International Standards Organization and the number is 266, and this actually defines all industry standard octave bands. But before I explain what are these bands, I will define 2 other things. So any octave band, let's say 3 hertz to 6 hertz, this is an octave band. Now this is not an industry standard octave band, but I just wanted to make a couple of concepts clear. Okay, it has a lower frequency limit FL and it has a higher frequency limit FU. So an octave band has a lower frequency limit and a higher frequency limit, and the ratio of FU over FL equals 2. And then there is also a central frequency FC. So it's not a, so there's a lower frequency limit, there's an upper frequency limit, and there's a center frequency. Now center frequency FC is not equal to FL plus FU over 2. You don't take the average of these two. Rather, what you do is that the proportion of FC and FL and FU and FC has to be same. Okay. So FC over FL should be same as FU over FC. Okay. So in the same proportion, the value has to go up. So what that means is that FC square equals FU times FL square root of that. Okay. So there shouldn't be a square sign here. So this is how you calculate the center frequency of an octave band. And if you do the math, you will find that FC equals 1.414 times FU and this will be FL and FU is equal to 1.414 times FC. Okay. So now I am going to specify different octave bands. Each octave band I am only going to specify its center frequency, and then for that octave band, if I specify the center frequency, you can calculate using the relations we discussed earlier, its upper frequency limit and the lower frequency limit. So ISO 266 octave bands. So I am going to just specify their values of FC. Okay. So the first octave band's center frequency is 1 Hertz, and then 2, 4, 8, 16, 31.5, there's a little difference here, 63, 125, 250, 500, 1000, 2000, 4000, 8000 and 16,000. So these are all center frequencies. So okay, and each of this band also has a band number. Okay, so the band number of this guy is 0. What is the meaning of this band number? We'll see it later, but for the moment just remember that it has a band number. The band number for the second octave band, which has a center frequency of 2, so this is 3, this is 6, this is 9, this is 12, this is 15, this is 18, and I am going to complete this series. Okay, so this is my center frequency, this is my band number, this is band number, this is band number, and these are center frequencies. Okay, so a lot of times in the industry or in scientific literature, you will be expected to produce your results related to noise measurements, and initially you will have a time series data, then you may FFT it, and then the expectation will be that you further change the form of that frequency domain data and you report data at these specific center frequencies only. Okay, because then you can see more cleaner information. There will not be at 20,000 a lot of points. There will be cleaner information and people can compare your results with their results. How you do that we will discuss that later, but right now this is what I wanted to discuss. Now suppose you want to report the results. So how do you report the results? On graph. Okay, so on the x-axis again you will have frequency, and on the, let's say on the y-axis you want to plot decibels. You want to plot decibels. And suppose you want to report results for all these octave bands. So what you do is you can first list them. So this is 1, 2, 4, 8, 16, 32, or was it 31.5? 31.5. So I am going to round off here, but it should be actually 32, 31.5, 63, and so on and so forth. Okay? And then whatever is the SPL corresponding to these frequencies. Now this SPL is not the value of pressure at that particular frequency, but it is the pressure due to all the energy which is contained in this octave band corresponding to 1 Hertz band. That is the number you are going to put. Okay, when you do FFT, you will get some value at 1 Hertz. That is not the value you are going to put on this graph. Rather, you will see what is the total energy in this octave band. There will be some SPL corresponding to that, and that SPL you are going to put it here. How will you calculate it? We will discuss that later. But the point what I am trying to make is that this value is not directly taken from the FFT of the signal. It will require further processing. So you may get different values. Okay. So you can plot these and then you can connect them. So on and so forth. Okay. Couple of things when you are making this kind of a graph. Look at the spacing between different center frequencies. Spacing on x-axis between successive octave bands central frequencies is same. Essentially what that means is this is a logarithmic scale. The spacing between 1 and 2 is not double, half of that between 2 and 4, and so on and so forth. It's the same thing. Okay? So this is important to note. Okay? Typically, a lot of times, so these are the ISO standard octave bands. A lot of times when we report data on noise, most of the times we start from 63 Hertz and then we go up to 5-10,000 Hertz or so, something like that. Because there is low frequency noise, most of the times we cannot listen. In some cases we may also start from 31.5 Hertz. Most of the times we are worried from 63 Hertz and upwards. Okay? So this is the other thing. So understood? So this is what octave bands are. Then now in octave bands the central frequencies are spaced by a factor of 2. Now people can say that, oh, this resolution of between frequencies is very large. I want finer information. I want finer information. So then there are 1/3 octave bands. Okay. So how do you calculate these 1/3 octave bands? Their center frequencies, you again start from 1 Hertz. That is the first center frequency. So this row is FC. First is 1 Hertz, and there is a formula for it. And why it is 1/3, we'll talk about it later. But the formula is that FC is equal to 10 to the power of n over 20. So you use this formula. Okay. So when n is equal to 0, Fc is 1. Okay. When n is equal to 2, this thing is 1.25. When n is equal to 3, this is 1.6. N is equal to 4, this is 2. Okay. So I will write down these values. So 2, 2.5. So I am writing down approximate values. 4, 5, 6.3, 8. And when n is equal to 10, it becomes 10 hertz. Okay. Excuse me, when n is equal to 20. When n is equal to 20, then 20 over 20 is 1. This becomes 10. Okay. So you use this relation to calculate these frequencies. Now you would think, so actually let me show you a graph. So these are what I am showing here are different values of center frequencies. Okay. So let's look at this blue line. This is log, okay, so I am sorry, it should be log n over not 20, it should be n over 10. I don't know, I was wrong, that's why it was not matching up. Yeah. So let's say n is equal to 20, you start from n is equal to 20. So then 20 over 10 is 2, 10 to the power of, okay. So this is 100. This is 100. This should be 10 to the power of, I have to correct this, 10 to the power of, yeah. So when n is equal to 20, I get 100 hertz. When n is equal to 30, I get 1000 hertz. And all the intermediate frequencies I get like these. These are the mathematically correct values of frequencies. 100, 125.89, 158.49, 199. And so on and so forth. Okay. So, but you don't use these long numbers for practical considerations. So you basically put some nominal. So these are the exact values generated by ISO standard. And then ISO says, okay, you don't have to worry about 125.89 hertz. You can be happy with 125. So these are the nominal values specified by ISO. So this is also in blue. Okay. So these are the values of center frequencies. There is also a red line, we'll talk about it later. Okay. So 100, 125, 160, 200, 250, 315, 400, 500, 630. So what does that mean? That every time n goes up by a factor of 10, I move out 1 decade, right? Here n is 20, here n is 30. So n has gone up by a factor of 10 and I have gone up by 1 decade of frequencies. Okay. Now, interestingly enough, when you look at the mathematics, if you multiply this starting frequency 100 by 2 to the power of 1 by 3, what is the number you get? 125.99. This is what, when you do this, 158.74, 200, 251.98, 317.48, 400. This should be actually exactly 400, and so on and so forth. So these frequencies in red and blue, they are pretty close for practical considerations. That is why this is known as 1/3 octave band. Because if you are constructing 1/3 octave band, you will have to multiply 2 to the power of 1 by 3. And when you, the values which you get are, they are pretty close to these values. And then you make sure that once you reach the other end, you again round it off to 1000. And then you again start the next cycle. Okay, that is what 1/3 octave band central frequencies, this is how they are calculated. They are calculated based on this 10 to the power of n over 10 formula, and then you round it off to get their nominal values. Last thing, you look at these n's, n equals 20, 21, 22, 23, 24, 24. These n's are called band numbers. So in the last, earlier when I was discussing octave bands, right, I had just mentioned that each band is associated with a number, right? So these are the band numbers. So whenever my frequency goes up by a factor of 2, see this is 100 hertz, this is 200 hertz, n goes up by a factor of 3, not 3, by 3. Again, when I go to 400, it goes up again by difference of 3, and so on and so forth. So you understand this? So these are the industry standard ISO octave bands. So, and the band numbers of octave bands are same as if you calculate using 1/3 octave formula. Okay. So band number 1 is 1.25, 0 was 1 hertz. Okay. 1 is 1.25, and this is the range of frequencies. This is the the lower frequency limit, upper frequency limit for the center octave band. This is the second 1/3 octave band, not band numbers 2, and this is band number 3, and this also is this 2 also happens to be the center frequency of this octave band. This is an octave band, these are all 1/3 octave bands. Okay. So this is the frequency range for this octave band. Then you have two more octave band, 1/3 octave band, then you get the second, third, another octave band, then you have some more 1/3 octave bands, then you get another octave band, and so on and so forth. Okay. So this is, so it starts, band number starts from 1. So once you have the band number, actually you can calculate the center frequency, upper frequency, all that stuff very easily. So band number is all what you want, and then you can calculate everything in this table. And then of course you have to round it off to meet some practicality considerations. So you can go up till 20,000 hertz, and you will have, so there are a total of 43 plus the first of 1/3 octave band was number 0, so total of 44 1/3 octave bands in the whole system. See, here we started from 1.25, it should have started from 0, right? So this is how it goes. So you understand that? Now last point. So we have talked about octave bands. Then we have talked about 1/3 octave bands. And so this is, you have finer resolution. Then there are finer bands also. There is 1/10 band. Okay. Here, then you have 1/12th, then you have 1/15th, and you have 1/30th. Okay. Now in 1/3 octave band, delta F. What is delta F? The difference between F U minus FC. That is delta F. This is approximately equal to 23% of FC. If you do the calculation, you will find that it is about 23% of FC. For 1/10th band, this number is about 6.9%. For 1/12th band, this number is finer, 5.8%. Then you have 1/15th, it's 4.6%. And then 1/30th band is 2.3%. I have to write this clearly, so this is 1/30th band. And then there is also a 1% band, where this delta F is 1% of the bandwidth, and you can calculate. So it's not that there are only two types of bands, octave band and 1/3 octave band. There are lots of bands, but most of the times in industry you will see octave and 1/3 octave. But if you really want to hone in and take a finer look at the results, you can go to finer resolutions also. Okay. So this is what I wanted to discuss in this class. In the next class, what we will discuss is how to generate results for these octave bands using our time series analysis. Okay. Thank you.